6 minutes ago, somewhere in the Chilean mountains, a machine the size of a small car took another picture of the night sky. At first, that sounds completely ordinary. Humanity has been taking pictures of the universe for centuries, but this telescope does something that almost no telescope before it was designed to do. It remembers. It remembers what the sky looked like yesterday. It remembers what the sky looked like last week. And when it takes another picture tonight, it compares the new image with everything it has seen before. A star becomes brighter, an asteroid moves, a galaxy suddenly erupts. A new object appears, or something that was there before simply disappears. And the moment the telescope notices a change, the universe sends an alert. This is the Vera Rubin Observatory, and it has barely begun its real mission. But its earliest observations have already revealed things that astronomers never expected to see so quickly. A river of stars stretching farther than the entire width of the Milky Way, an asteroid the size of a skyscraper spinning so fast that scientists never expected something that large to remain intact. A possible star that may have collapsed into a black hole without exploding, and a visitor from another solar system that had already passed through our cosmic neighborhood before anyone realized it was there. And remember, these are not discoveries from the end of Rubin's mission. This is the beginning. Some of these discoveries came from test observations. Some came from early commissioning data. The telescope was still being prepared, still being tested, still learning how to operate at full capacity. And it was already finding things that previous generations of telescopes had missed. So the real question is not simply, what has Vera Rubin discovered? The real question is this: if this is what the telescope found while it was warming up, what is waiting in the next 10 years? Because on June 30th, 2026, after decades of construction, engineering, testing, and delays, the Vera Rubin Observatory officially began its real mission. The mission is called the Legacy Survey of Space and Time, and the idea behind it is almost impossible to comprehend. Every few nights, Rubin will photograph the entire visible southern sky, not one galaxy, not one star, not one carefully selected target, the entire sky. Then it will compare the new images with the old ones, and if even one tiny point of light has changed, the system can flag it. A star gets brighter, an asteroid changes position, a supernova explodes, a black hole is born. An interstellar object enters our solar system, or something that should be there is suddenly gone. At full operating speed, Rubin is expected to generate around 7 million alerts every single night, 7 million every night. That number is so large that it changes the nature of astronomy itself. This is no longer simply a telescope collecting photographs. It is a live monitoring system for a universe that never stops moving. For most of human history, the night sky appeared permanent. The stars seemed fixed, the constellations seemed frozen, the universe appeared so slow and so enormous that a human lifetime felt too short to notice anything important changing. But the universe was never still. Stars were exploding, galaxies were colliding, asteroids were crossing our planetary neighborhood, black holes were forming, and objects from distant solar systems were passing through ours. We simply did not have a machine capable of watching the sky often enough to catch these events as they happened. Now we do. And Rubin's early observations have already shown what happens when the sky finally gets a memory. In June 2025, the world received an early preview of what this observatory could see, using only around 10 hours of test observations collected across several nights. Rubin produced an enormous composite image of the Virgo cluster. Inside that single image were approximately 10 million galaxies, not 10 million stars. 10 million galaxies, and every one of those galaxies can contain billions of stars. Now think about that for a second. A single image. 10 million galaxies, and that image represented only a tiny fraction of what Rubin is expected to observe during its full 10-year survey. The long-term goal is roughly 20 billion galaxies, 20 billion. Humanity has spent thousands of years looking at the stars. We built observatories on mountains. We launched telescopes into space. We created entire branches of science dedicated to understanding what is out there. And when Rubin finally opened its eye and the first major images already contained millions upon millions of galaxies, but the galaxies were not the only surprise. Hidden inside those early observations was a structure that had escaped previous surveys, a massive stream of stars, a river of stars stretching approximately 163,000 light-years. That is longer than the diameter of the entire Milky Way. The stream was associated with the spiral galaxy Messier 61, and it had been sitting in the sky, waiting to be noticed. This is what makes Rubin so different. The Hubble Space Telescope gives us incredible detail. The James Webb Space Telescope looks deep into infrared light and allows us to study the ancient universe. But Rubin is built around a different question, not simply what is out there, but what changed. Imagine taking one photograph of a city. You can see the buildings, the streets, the lights, everything that exists at that exact moment. But take another photograph tomorrow, and suddenly the city begins to tell you a story. A building has collapsed, a fire has started, a vehicle has moved, a new structure has appeared. The city is no longer just an image, it has become a timeline. Rubin is doing something similar with the universe. It is turning the sky into a time lapse. And the universe is already beginning to reveal what it has been doing while nobody was watching. But one of Rubin's earliest discoveries created a completely different kind of problem. Because this time, the object was not enormous, it was an asteroid, and it was spinning far too fast. Its name is 2025 MN45. On paper, it sounds like another piece of rock orbiting the sun, but then astronomers measured its rotation. The asteroid is approximately 710 meters across. That is nearly twice the height of the Empire State Building. Now imagine something that large rotating in space. You might expect it to take hours, and perhaps even days, to complete one full rotation. But 2025 MN45 completes a full rotation in approximately 1.88 minutes. Less than 2 minutes, a rock hundreds of meters wide spins completely around before most people could finish making a cup of coffee. And that creates a serious problem because many asteroids are not solid blocks of metal. They are rubble piles, loose collections of rock and dust held together mainly by gravity. Imagine a giant pile of gravel floating in space. Now spin that pile faster and faster and faster. Eventually, the material at the surface begins trying to fly outward. The faster the rotation becomes, the harder it is for gravity to keep everything together. For an object this large, scientists did not expect such an extreme rotation speed. A rubble pile rotating this quickly should be at serious risk of breaking apart, but 2025 MN45 is still there, still intact, still spinning. So what is holding it together? One possibility is that it is not an ordinary rubble pile at all. Researchers have suggested that the asteroid could be a fragment of a much denser planetary body that existed during the early history of our solar system. Billions of years ago, large planetary objects collided. Some were melted, some were shattered, some disappeared completely. And 2025 MN45 may be a surviving piece of one of those ancient worlds, a fragment of a planet that no longer exists, still orbiting the sun after roughly 4.5 billion years. And humanity only just noticed it, but this asteroid was not alone. The same research identified 19 newly confirmed fast-rotating asteroids. 16 were classified as extremely fast rotators. 3 were even more extreme. And here's what makes the discovery even more remarkable. The data did not come from decades of searching. It came from only a small number of nights during Rubin's early commissioning phase. The telescope was still being tested. It had not even begun its full 10-year survey. It was warming up, and during that warm-up period, Rubin helped identify more than 11,000 previously unknown asteroids in only a few weeks. Scientists expect the full survey could eventually discover around 1 million previously unknown asteroids during its first full year, 1 million new pieces of the solar system. And these are not just random rocks to add to a database. Asteroids are fossils. They are pieces of the early solar system. They preserve evidence of the collisions, movements, and transformations that eventually created the planets we know today. Some could reveal how the outer planets moved into their current orbits. Others could be fragments of planetary bodies that disappeared billions of years ago. And some may be important for a much more immediate reason. They could be headed toward Earth. One of Rubin's most important abilities will be detecting small objects that are difficult to see until they are already very close to our planet. Some may be only a few meters across. They may not destroy civilization, but they can still produce enormous explosions in the atmosphere. And if Rubin detects one early enough, scientists may know that an impact is coming days before it happens. They can prepare instruments, point sensors toward the correct location, and watch the event in real time, instead of studying the impact after the fireball is already gone. But the strangest things Rubin is finding are not always things that appear. Sometimes the most important discovery is something that disappears. For decades, astronomers have theorized about failed supernovae. When a massive star reaches the end of its life, it can explode in one of the most powerful events in the universe. For a brief moment, a single supernova can become brighter than an entire galaxy. But some massive stars may not explode at all. Instead, the core collapses inward, the star disappears, and a black hole is born. No enormous explosion, no spectacular flash, no cosmic fireworks, just a star that was there, and then suddenly was not. That is why detecting a failed supernova is so difficult. Astronomers are not looking for something bright, they're looking for an absence. They are searching through a universe filled with billions of stars, trying to determine whether one of them has quietly vanished. Early Rubin-related observations have already helped astronomers identify a possible candidate in the Andromeda Galaxy, approximately 2.5 million light-years from Earth. They've confirmed it could provide evidence that some massive stars collapse directly into black holes without producing a traditional supernova, and that could change how scientists estimate the number of black holes in the universe, because if stars can disappear silently, there may be far more black holes out there than we have ever detected, and this is exactly the kind of event Rubin was built to find. On one test night, the observatory generated hundreds of thousands of alerts from a single region of the sky. Once the full survey began, that number expanded dramatically. Millions of alerts. Every night, every changing object becomes a potential clue. But there is a problem. No human being can examine 7 million alerts every night. It is impossible. So Rubin is creating something almost as important as the telescope itself. A global system of automated tools designed to filter the flood of information. The observatory is not just taking pictures, it is building a nervous system for the sky. And some of the most important targets in that system are exploding stars. Type 1a supernovae are especially valuable because astronomers use them as cosmic distance markers. In the late 1990s, observations of distant supernovae helped reveal that the expansion of the universe is accelerating. Something appears to be pushing the universe apart. Scientists call that mysterious influence dark energy, but the exact nature of dark energy remains unknown. Rubin could find hundreds of thousands of Type 1a supernovae every year, and that enormous increase in data could help scientists investigate one of the biggest disagreements in modern cosmology, the Hubble tension. Measurements of the early universe and measurements of the modern universe do not appear to perfectly agree about how fast the universe is expanding. Maybe one of the measurements is wrong, or maybe something fundamental about our understanding of the universe is incomplete. Rubin may help determine which possibility is correct. But the telescope is not only watching things inside our solar system, it is also looking for visitors from outside it, objects that formed around other stars, objects that were thrown out of their original solar systems and spent millions or even billions of years drifting through interstellar space. Eventually, some of them pass through our solar system, and most of the time, and we have no idea. One of the most recent interstellar visitors was the Comet 3 I/Atlas. It was announced in 2025 after being detected by another telescope network. But when astronomers went back through Rubin's archived observations, they discovered something remarkable. Rubin had already photographed the object 10 days before the world knew it was there. The visitor had already passed through our cosmic neighborhood while sitting inside existing telescope data. Nobody had recognized it in real time. And this may be one of the most important things about Rubin. The telescope does not only discover the universe when something happens, its data can be searched again and again and again. An object nobody recognizes today, it may become incredibly important tomorrow. A strange point of light may turn out to be an asteroid. A faint object may come from another star system. A star that disappears may reveal the birth of a black hole. The more images Rubin collects, and the more powerful those comparisons become. But everything we have discussed so far is still the visible universe, the galaxies, the asteroids, the supernova, the interstellar visitors. All of them produce or reflect light. The real mystery is what we cannot see, dark matter and dark energy. Together, these invisible components dominate the universe. And the observatory named after Vera Rubin is uniquely connected to that mystery. In the 1970s, Vera Rubin studied the rotation of galaxies, and she discovered something that did not make sense. Galaxies were rotating so quickly that the visible matter inside them should not have been enough to hold them together. Based on what astronomers could see, the galaxies should have been flying apart, but they were not. Something invisible was creating additional gravity. That invisible substance became known as dark matter. Vera Rubin never got to see the observatory carrying her name begin its 10-year mission. But in a very real sense, the mission continues the question her work helped create. What is actually holding the universe together? Rubin will search for answers by mapping billions of galaxies. As light travels through the expanding universe, it is stretched. That stretching creates a measurable shift. By studying those shifts across enormous numbers of galaxies, scientists can build a map of the universe across space and time. And by studying the way galaxies are distributed, They can investigate the invisible gravitational structure surrounding them. The goal is not to photograph dark matter directly. Dark matter does not shine, it does not reflect light, it does not announce itself. Scientists can only detect its effects, the way it bends light, the way it influences galaxies, the way it shapes the largest structures in the universe. And Rubin could provide one of the most detailed maps of that structure ever created. At the same time, the observatory will investigate dark energy. Is it constant? Has it changed throughout the history of the universe? Will it continue to accelerate cosmic expansion forever? Or is our current understanding of gravity incomplete? These are not small questions. The answers could change what scientists believe about the ultimate future of the universe, and this is why the first images from Vera Rubin matter so much. Because the telescope has barely started. During its early observations, it already revealed millions of galaxies, a stellar stream longer than the Milky Way, asteroids spinning at speeds scientists did not expect, thousands of previously unknown objects, a possible star that collapsed without exploding, and an interstellar visitor that had already passed through our solar system unnoticed. Now, with its full 10-year survey underway, Rubin is expected to generate millions of alerts every single night. The sky that once appeared still is about to become a constantly changing movie. For thousands of years, humanity looked up at the stars and imagined that the universe was permanent. Now we know better. Stars die, galaxies collide, asteroids move, black holes are born, objects from other solar systems pass through ours, and sometimes something that was there yesterday is simply gone today. The universe was never still, we just lacked the technology to notice. Now, for the first time, humanity has built a machine designed to remember what the sky looked like before. And that may be the most important thing about the Vera Rubin Observatory. It is not simply giving us a sharper picture of the universe, it is giving us a record of the universe changing. And if its early observations are any indication, the next 10 years could completely change what we think we know about the cosmos. Because if Rubin can find this much during its early observations, what will it find after 5 years? What will it find after 10? How many silent black holes are waiting to be discovered? How many interstellar visitors have already passed through our solar system without us noticing? How many asteroids are moving through the darkness right now, and what happens when the telescope finally finds something that does not fit any existing explanation? Because that may be the real story of Vera Rubin. The telescope is not simply going to confirm everything we already believe, it is going to show us what we missed, and if the first discoveries are any indication, the universe has been hiding far more than we ever imagined. So the next time you look up at the night sky, remember this. The stars above you are not frozen, the universe is not silent, and somewhere in Chile a machine is taking another picture, then another and another, comparing the sky of today with the sky of yesterday, waiting for something to move, something to appear, something to disappear, or something completely unexpected to enter the frame. The Vera Rubin Observatory has 10 years to watch the universe change, and if the first discoveries are any indication, we may be about to discover that the most important things in the universe were never the things we were looking for. So tell me in the comments, which discovery shocked you the most? The skyscraper-sized asteroid spinning in less than 2 minutes, the star that may have disappeared into a black hole without exploding, the river of stars larger than the Milky Way, or the interstellar visitor that had already passed through our solar system before anyone realized it was there, because this is no longer just a telescope watching the universe. For the first time, and the universe is being watched in real time, and now we finally have the technology to see what changes next. If you want to follow the discoveries that could completely change our understanding of the cosmos, make sure you are subscribed, because the Vera Rubin Observatory has only just begun. And the next picture it takes, you could reveal something humanity has never seen before.